I don't really talk about this, but a long time ago, there is a time when I really felt like lost. I really felt like I needed direction, I guess. Specifically, I was downtown and I ended up over here somewhere, and the place I was going was just over here, which I mean really isn't that far away. But you know how it is when you're lost. You don't know where you're going, and you don't just want to begin wandering aimlessly because then you're just going to end up feeling more overwhelmed and more lost. And so it was a bit of a novelty to do this at the time. But I took out my phone and not only was it able to show me a map, it was actually able to give me directions. It was able to route me to exactly where I needed to go. And not only was it able to distill all of the information in the map, including things that are irrelevant like the names of each building and the system of paths on the property of each of these buildings and whatever's going on in the harbor. Not only was it able to distill down all of those irrelevant details and only look at the fundamental information needed to solve the problem of getting me to where I needed to go. Not only was it able to give me a path to my destination, it was actually able to give me the best possible path, the one that would get me there the quickest. And I think it was around then that I realized that I really ought to learn about algorithms. This is a course about algorithms. I guess the first order of business in a course about algorithms is I have to tell you what algorithms are. I mean, that's as good a place to start as any, I guess. And so you know how it is. There's sort of a mathematical tradition of this, but when you have a new concept, you really want some complicated, equal parts exasperating and dazzling long definition that maybe you could memorize, and you can tell people you know about how you're studying this complicated concept, and they can sort of nod along, and at the end they can say, wow, it sounds like you're really smart. So we've got one of those definitions for algorithms. It's this one. An algorithm is a precise and unambiguous sequence of, okay, actually, you know what? So we do need formal definitions, and you're going to discover that we actually spend a lot of time wringing our hands in a course like this about having formal definitions of everything. Algorithms, definitions of mathematical concepts themselves, definitions of techniques to solve problems. We need those. On the other hand, the problem with formal definitions is we sort of need intuition before we can really appreciate why a complicated definition is necessary. So I have to break this down a little bit, but we really won't get to appreciate this definition for a few lectures. So the point of an algorithm is to describe how to do something. That's really the only definition we need for now. And I think going forward, that's the one you should keep in your mind. We need to have this. This needs to be available to us. It's good to be building things on a solid foundation. So having formal definitions is critical for that. But as far as on an everyday basis, what is an algorithm? It's a description of how to do something. Now, of course, when we think about that definition, there's a few questions that come to mind. One of the questions is, wait a minute, what does something mean? Well, an algorithm is a description of how to solve a problem, how to perform a task. I guess the first step to defining such a thing is to have a clearly defined task. If I can't explain to you what problem I'm trying to solve, why would you believe me when I explain a possible solution to that problem? And then when it comes time to solve the problem and I have a possible solution that I want to convince you is a good solution, or maybe a solution at all, that it works, I need to make sure I provide a precise and unambiguous sequence of instructions. That is, I need to describe every detail in such a way that you don't have to do my job for me. That the description I give gives you enough information to be convinced that my process actually works. And if I'm claiming that my process is better than somebody else's, why it is that it's so much better. Designing algorithms is, I think, exercises every aspect of the human brain. It requires human creativity. It requires cleverness. It actually requires tons and tons of patience. We're going to see that a lot. We're going to see that we really enjoy employing our creative abilities to design algorithms and solve problems. But a lot of the time, what we find ourselves doing is trying something, realizing it doesn't work, backing up, trying something else, realizing it doesn't work, backing up again. And so patience really comes in handy for that. And so to be an algorithm designer, to be the type of person that reasons about algorithms, you need those skills. But on the other hand, when it comes time to describe your algorithm to others, your job as the designer is to be creative and clever, not their job as somebody you're explaining it to. So if I give a list of instructions to you of how to perform some algorithm, it is up to me to demonstrate why they work and to explain to you in enough detail what you have to do to follow the steps. You should require no creativity or cleverness to be able to carry out the instructions for an algorithm. Often this is contextualized in a way like, oh, you've designed an algorithm. You need to make sure that you can explain it to somebody who knows nothing about computers. I've got a couple of issues with that. So one of them is, wait, who said anything about computers? Algorithms have been around way longer than computers have. Some of the algorithms that we're going to cover in this course predate modern computers or indeed the notion of a computer at all. There's nothing inherently computery about an algorithm, and there are lots of reasons to study algorithms that go far beyond things like writing code. Although, yes, it's true, we're probably going to implement a lot of the algorithms that we talk about in this course, and that includes me, and I'm actually going to do that later in this lecture. And so saying, oh, you can provide the instructions to a human who knows nothing about computers misses the point in a couple of ways. One of them is that, well, algorithms themselves are independent of computers. Another one is that we should give humans a bit of credit. If you can explain it to a human and they can follow the directions, that doesn't necessarily mean that no creativity or cleverness is required, because you have to give humans, even people that aren't computer science experts, some credit. Humans have a lot of inherent creativity and cleverness. It is true, though, that we often find ourselves implementing an algorithm as a computer program. And computers do not have inherent creativity or cleverness. I'm aware of the fact that in the last few years there have been various computer programs created that try to persuade their human users that they are somehow sentient or have creativity or cleverness, but they do not. Feel free to drop by the office and we can argue about that. But because computers have no creativity or cleverness, it is up to us to ensure that we specify algorithms in a way that they can be carried out by computers. And there's that old adage that says that the computer never does what you want, it only does what you tell it to. One of the reasons, though, that we have to specify algorithms at a level of detail that allows the steps to be carried out by a computer is because it turns out that much of our job as designers of algorithms, as people that analyze algorithms, actually has to do more with our human colleagues than computers. Implementing an algorithm on a computer is often the last step of the process. First, we have to design the algorithm, satisfy ourselves that the algorithm works, and probably then satisfy others that it works. Generally speaking, we don't want to write a bunch of code, deploy the code, have it be out there in the world, and only later ask the question, wait a minute, does this algorithm actually work? Is this algorithm actually an efficient solution to a problem? Usually we do all that stuff first, and that involves convincing humans, which means we should be specifying the algorithm in such a way that somebody who's a bit skeptical about our claims can easily verify or refute what we are saying. We owe it to them as our colleagues to make sure that we express what we are intending, our algorithm or our analysis of the algorithm, in a way that they can understand it. Another aspect that we should consider is the fact that if I describe a process for solving a problem, that process actually needs to be finite. It needs to require finite resources. If I describe a way of solving a problem that requires a computer with a potentially infinite amount of memory, then I guess I can't solve that problem. If there are cases where that problem requires an infinite amount of time, well, then I guess I can't solve the problem in those cases. So it turns out, I'll spoil it now, but we're going to get really hung up on running time in this course. We're going to spend a lot of time thinking about resources basically just as a surrogate for time. And it is true that of all the different resources we think about computationally, time is a pretty important one. But there are other resources out there. There are things like the memory of the computer, disk space, bandwidth, because a lot of the programs that we work with work over a network. Things like power consumption count as resources. But in any event, an algorithm, to be considered an algorithm, to even be a process we could describe as an algorithm, needs to require finite resources. Otherwise, it really isn't a solution to a problem. It's just a trick I can use to solve the problem in some cases. It's true that there are algorithms out there that require such an exorbitant amount of resources that they're not practical. That's a separate problem to us. So it's true, for example, that I could specify an algorithm that might take 1,000 years to run. It's probably true that you will not use my algorithm if that's the case, but it's still an algorithm because it still requires a finite, even though it's a large finite number of resources. It's also true, and it's worth considering, that studying algorithms and getting too hung up on how many resources something requires, as long as that number is finite, is a bit short-sighted. Because if we think back, if you go back 20 or 30 or 40 or 50 years into history, what we thought of as large inputs or impossible problems has changed a lot. Whereas previously, 50 years ago, we might consider the idea of working with an array of 1 million integers to be something that could only be done in a supercomputer. It's now something that's being done thousands of times per second on whatever computer you're using to watch this video. So what is considered a large number has changed quite a bit. And so I could invent an algorithm today that seems to require exorbitant resources and then discover in a couple of years that actually those resources are easy to come by. So an example of what not to do, if we want to claim something as an algorithm, let's take a look at this. Suppose that I describe to you, using this sort of English-like notation, a procedure that I claim is an algorithm to sort a deck of cards. And I'm going to sort of work backwards through all of the issues this has. The first sort of obvious one, if we look at the procedure, it says, okay, well, check if the deck is sorted. If the deck is not sorted, throw all the cards on the floor, pick them all up, and then I guess hope that you've sorted them. And if you haven't sorted them, just go back and do that again. And do it over and over and over and over again, and you may have to sit there for all eternity trying to sort this deck of cards via my process. It's also true that with pretty high likelihood, if we are all immortal and just have all eternity to sit here and try this out, eventually the deck of cards will be picked up and it will be sorted. It could happen tomorrow. It could happen in a billion trillion years from now. But if we have infinite patience and infinite time, which of course we don't, then this process will probably eventually result in the cards being sorted. But you can also imagine there is a universe in which I am the least lucky person imaginable, and that every single time for all eternity that I throw the cards on the floor, I pick them up in the wrong order. They are not sorted. So there is a chance, even if it's a slim chance, there is a chance that this process never finishes. And therefore, this isn't an algorithm. Well, what can we call this? I mean, will this successfully sort things sometimes? Yeah, it will. But can we rely on it to do so all the time? No, we can't. So maybe we could charitably, just in the interest of giving it a name, we can call it a heuristic. Because the rules for what it means to be a heuristic are a bit more lax than an algorithm. This is a trick that we can use that sometimes works. It's something to try. Now actually, this is not an algorithm because it does not require finite resources. The slide charitably points out that we could call it a waste of time, which is fair enough. But there are a few other aspects of it I should point out. So one of the other aspects of it is that actually I have never told you what I mean by deck of cards. I mean, that's sort of a big deal, isn't it? Now, this was deliberate. So I talked about sorting a deck of cards. And I'll bet that many of you, when you hear the term deck of cards, imagine the same thing that I imagine when I hear that term. And I mean, we're all familiar with the idea that cards can be put into a deck. But which cards am I talking about? I haven't explained that. So that's already a problem. Even if this were an algorithm, that would already be a serious problem. It wouldn't really meet our definition. The other problem that I guess is sort of hiding underneath that is, what does it mean for a deck of cards to be sorted? If you think carefully about whatever deck of cards comes to mind when you think of cards, is there one obvious sorted order of that deck of cards? Because if the answer is no, then I really needed to explain that as well. So this is really a bit of a problem. We have to do better than this. We need a process that's clear and unambiguous, that anybody can perform, and that anybody would be able to understand if they were performing it. If you don't know what it means to sort it for a deck of cards to be sorted, then how will you verify that the deck is sorted? And of course, we need our process to require finite resources to be an algorithm. Well, I guess we should begin talking about some actual algorithms at some point. So here are two problems. And I've laid the problems out formally, but there actually are some details, even of these problems, that are left as unknowns. And that's because we sort of have to start somewhere. I mean, it's not worth it for me, and neither for you nor for me, to waste a bunch of time deriving all of mathematics from scratch. There are some things we have to assume. So I'm not going to define what addition is. I think if you look it up, you'll figure out a definition if you need one. I'm not going to define what it means for something to be an array. I'm going to make the assumption that all of us coming into this course have a certain amount of common background. We've all taken 1 year worth of computer programming probably. We probably have also taken a discrete math course or something that's equivalent to that. And therefore, if I use terms like array or integer, and I use variables like n, that we all sort of understand that we're speaking the same language. So the first of my two problems to solve is called pair sum 225. And it takes as input an array, which I will call A, of n integer values. And it returns true or false. That's all it returns. It doesn't actually have to provide evidence of why it came to the answer it did, although if I design an algorithm for it, it is my responsibility to prove, to show that that algorithm, when it generates an answer, is generating the correct answer. And the answer is yes or no, and the answer is yes if somewhere in that array, there are two elements that add together to equal 225. And it's sort of implicit in the description, and you might be able to see why. But I don't have to worry too much about I and j being equal. It's actually not going to be possible for there to be a case where AI plus AI equals 225. And the reason is that the array contains integers, and that for AI plus AI to equal 225, that would mean that 225 over 2 would have to be an integer, which it isn't, because 225 is an odd number. So it's implicit in this description that I and j can't be the same number for the answer to be true. Now, the second problem, ContainsDuplicate, is actually very similar, and this is deliberate. We're going to notice that the algorithms we can come up with to solve these two problems at first are pretty similar. The ContainsDuplicate problem takes an array of n integers, and then it returns true or false. It returns true if there are any two distinct indices of the array where the elements at those indices are the same. And so, of course, here we do care about the idea that I and j can't be the same. Otherwise, every array would produce the answer true, because if I have an array where I'm allowed to have an element in itself be considered a duplicate, then the first element of every array would be considered a duplicate with respect to itself. So in this case, we we require that the index I is not equal to the index j. All right, well, pair sum 225, the first of those problems, happens to be an example of something called a decision problem. Now, I mean, it's in bold, so I guess that means we all know it must be vocabulary, although I don't think that the term decision problem occurs again in this course for quite a while. And it's not a terribly difficult term to think about, but I've put it in bold anyway. It's something to consider. We often solve problems that are essentially just yes or no answers. And although it's my responsibility as an algorithm designer to show why my algorithm works, in this example, although it's easy for me to justify to you that a pair exists by showing it to you, the algorithm itself only has to return true or false. So in some examples here, this array, the pair 150 plus 75, that equals 225. Notice how easy it is if I show you a pair that I found for you to verify that I'm correct. All you have to do is verify that the two elements I told you about actually exist somewhere in the array. And so the answer is true on that array. The answer is false on this array. Even though the number 225 is in there, there aren't two separate values that add to 225. In this array, the number 225 and 0, those numbers are both in the array, so the pair does exist. But up here in this array, it does not. I could write some code to solve this problem. I could implement an algorithm in, let's say, Python to do this. So pair sum 225 is a Python function. It takes something called A, which I guess from context we know to be the array A in the problem specification. Although right off the bat, I've got a bit of a problem here, because it isn't really appropriate to call this thing an array in Python, because the basic internal types of Python don't include anything called an array. I mean, there are modules you can import that have things called arrays, but the built-in data types in Python include things like lists and dictionaries and primitive types like integers and sequence types like strings. But okay, so we'll call this thing an array. We then iterate over all the elements in the array A twice with two nested loops. So we iterate over all the elements and call them X, and then inside that loop look at all the elements and call them Y. And then just inspect them. There's a little typo in the slide there. There should be a colon there. And then if we find two elements that add to 225, then the answer is yes, and we return true. Otherwise, we get all the way to the bottom and we haven't found anything, so we return false. Now, if you're not a Python person, you're probably looking at this and beginning to panic because you're worried that we're going to spend a whole course talking about Python code, even though you don't know Python. Well, don't worry too much because I've got some of that for everybody. Suppose you don't want to write it in Python, maybe you want to write it in C. Okay, well, here's a C function that I claim implements pretty much the same algorithm as the one on the previous slide, the Python one. And the function here takes an integer n and an array of size n, and then it iterates over using two nested loops all of the elements in A with two indices, and then asks if any two of them add together to equal to 25, and then returns 1, because in C we don't have a native Boolean type, we only have integer types, and then if it finds a pair, and then 0 if it doesn't. Now, if you're not a C person, you're probably looking at this and beginning to worry a little bit because you were really loving that Python a minute ago, but now we've got C, and what's going on with the word int showing up everywhere, and why do I have to provide two arguments to the function? Okay, fair enough. Well, I've got to try and offend everybody equally here. So there's a third variant I could write. I could write it in Java too. Now, if you are a Java person, probably you weren't too uncomfortable with the C code and vice versa. C people can usually look at Java, and if they squint their eyes a bit, they can see pretty much what they're used to seeing. This Java code takes an array as the argument to the function, and then it is able to ask for the length of the array, and then it basically we run the same two nested loops we have in the C version. But we have a bit of a problem on our hands, which is that although all of us coming into this course know about discrete math and we know about programming to some extent, we may not all know the same languages. Odds are all of us know probably two languages by now, probably Python and Java, or Python and C and Java, or C++ and Java, or something like that. However, if we want to spend the entire course talking about code, and I mean, one of the natural ways of describing an algorithm is to write essentially code for that algorithm. If we want to spend the whole course talking about code, what do? Do we just choose one language and only use that? So do we decide we're going to write all of our algorithms, we're going to specify them all in Java, or we're going to specify them all in Python? I want to argue that that's a bit dangerous. It's dangerous for a bunch of reasons. So one of the reasons is that the goal at this level of designing and analyzing algorithms is often not to communicate with a computer, although again, we will implement code at various points during this course. It's to communicate with humans. I want to write my algorithm down in a way that it's readable to humans. Now, you could argue that a human who knows Java could read Java code. But if you're actually a Java person or a C person or a Python person, deep down you also know that even if those are your favorite languages, there is some code you can write in them that is really ugly, and you really don't want to look at it, and you especially don't want to look at somebody else's ugly code and try and analyze it or make heads or tails of how it works. So I think what we should do is take a different option. I would argue that an algorithm is independent of a programming language, and I can prove that in a lot of ways. One of the easiest ways of justifying that claim is to observe that we've had algorithms for thousands of years, certainly for thousands of years longer than we have had programming languages. So therefore, clearly algorithms don't depend on programming languages to exist. It's risky to fixate on one language when we analyze algorithms because over time we become a bit habituated to the language. We begin to pick up on idiosyncrasies of the language, and maybe the lines get blurred between something the language is just naturally good at and something that is easy in a mathematical sense. So for example, if we go back to our Python code here, Python is a high-level language that does a lot of work for us, and we have this statement for x in A. I mentioned a few minutes ago that we don't even know what A really is. And one benefit of using Python is actually we don't care, because as long as A is iterable, we can iterate over it in Python. So I say for x in A, so yield every element in this sequence A. What is that actually doing behind the scenes? If I care about correctness or I care about performance, wouldn't I care about what's happening when I write for x in A? And if I spend too long analyzing algorithms in Python, I'm probably going to begin taking some of the wonderful convenience that Python offers me for granted. I'm going to forget about all the work going on behind the scenes to make for x in A something that I can do. So I want to be careful not to sort of lodge myself too deeply within the context of one language when I'm talking about algorithms. So actually, okay, the slide was about to say the thing I was about to say. The slide's observing that in this case, I already mentioned there's something suspicious about this thing A. It's probably the case, and I'm realizing as I read this that it's not, doesn't say it in the function anywhere, but I always envisioned that I would probably call this function with syntax sort of like this. So here's my array, there it is, and then I say, then I just call my pair sum 225 function, and I give it a. So in this case, a would be a Python list. Python lists are rather complicated. And are you sure you know what's really happening with a Python list behind the scenes? We hear the word list and we think of certain things, that we get a throwback to first year programming. We think about stuff like linked lists. But a Python list isn't a linked list. It's something else. And it's got very pleasant, somewhat complicated, but quite pleasant, convenient behavior. And I don't know if I want to go around analyzing algorithms using only Python, because I might be taking that behavior for granted and it might have a major impact on my result. I want to write algorithms that are agnostic of any particular language. And there are lots of different reasons that I can make that argument. One easy one is, if you go back 30 or 40 years, the languages they might have been writing code in during an algorithms course were completely different. They might be languages that nobody uses anymore, or languages that are used but that nobody wants to use anymore. So we're going to use in this course something called pseudocode. And one of the first things I want to tell you about pseudocode is that pseudocode is not a language. It's true that I will attempt to the best of my ability to make all of the pseudocode that I write consistent in this course. For your convenience, I guess, for our mutual convenience. But pseudocode isn't a language. There is no pseudocode compiler. And if you go looking at different sources, lots of different algorithms-related sources use pseudocode, and there's no requirement that somebody else's textbook or paper about an algorithm use the same type of pseudocode as I do, or that you do. There is a requirement in the course, a reasonable operational requirement, that if you write pseudocode, I have to be able to read it, and vice versa. But pseudocode is basically just an extension of English. It's a way of writing English and peppering it with mathematical notation wherever that's convenient. So in these lectures, we will typically use the pseudocode we write will typically look sort of like this, and it will basically be a combination of English and mathematical notation, and the control flow that we choose to use, things like this for and end for construction, are sort of C-ish. They're the kind of things you'd expect from a member of the C family of languages. And I should observe that Java and C++ and Python are all descendants of the C language in some sense. Now they have other progenitors as well, but they're all descendants of C. It's also an interesting observation to make is that if you go looking at algorithms textbooks or papers on algorithms, you will discover that a lot of them do seem to format their pseudocode similarly to this, like down to small minutia, like the word for is in bold, and then this stuff isn't in bold, and then there's the word do. The reason for that is not that we all got together and conspired to have some uniform standard for pseudocode. The reason for that is simply that we are probably all using the same typesetting software. So across math and physics and computer science and engineering, you often find that people are writing papers and textbooks using a system called LaTeX. And I know that I'm not spelling it perfectly correctly because the actual characters are more complicated than this. But the LaTeX system, there are macros available for it to render pseudocode, and I am using some of them in these lectures, and lots of other people use them when they write books and papers as well. However, pseudocode is very malleable, and we can take lots of liberties with syntax using pseudocode. So in my pseudocode, I will use this left-pointing arrow as an assignment operator. The reason I want to do that is because in programming languages, we often have this problem where we need to have two different operators involving the equal sign, one for assignment and one for comparison. And that's all well and good because I only have a certain number of characters on my keyboard, but in pseudocode, where I have all of mathematical notation at my disposal, we might as well do away with that ambiguity. So assignment statements involve an arrow, and that means I use the equal sign only for comparisons. So the equals is a relational operator only. Because pseudocode isn't actually a real language, it's a communication device, I am allowed to, whenever I want, take liberties with the syntax. Now, it's important to understand that this isn't really a blank check. I'm not allowed to, you could argue that reductively, I could just say, okay, fine, I'm allowed to take liberties with my syntax. I'm just going to write a one-line function in pseudocode saying, solve the problem and return the correct answer. But of course, somebody reading that would look at that and say that's, you haven't actually demonstrated how to solve the problem here. So while I'm allowed to take liberties with syntax, it is always my responsibility as the designer of the algorithm to convince others by making sure the pseudocode is detailed enough where it counts, to convince others that my solution is correct, and in cases where efficiency is at issue, that my solution is efficient. So one example of a liberty that I've taken with this pseudocode is when I want to know the length of the array, I just write n gets the length of a. I mean, and we understand, because we all agree that this is a plausible thing in most languages. So in the C language, it's a bit annoying, but in Java or Python, there are easy ways of figuring out the length of an array. And in C, I could write my function in such a way that the length of the array is available to me. Because we all agree this is something that is plausible and something that is relatively straightforward, then it shouldn't be controversial for me to just write n gets the length of a, because my audience, people reading this, wouldn't think that I'm trying to slip something past them with this. Of course, that's because the length of the array isn't really that important to the algorithm, besides that I need to know the length of the array to iterate over all of the indices of the array. The actual algorithm to solve the problem I specify in greater detail, pretty close to what I would write in actual code in an imperative style language, because it's important to me that my reader understand exactly how I am solving the problem. Okay, let's talk about the ContainsDuplicate problem. So it's also a search-based problem, I guess, although there's nothing in it that requires an algorithm that solves it to do any searching. It's true, frankly, that if you actually want to solve it, you probably will search through the array, look at the elements to find duplicates. So we look through our input array and we decide whether there's any element that appears more than once. So in this first example, the element 50 appears more than once, and so the result is true. In the following example, there are 4 elements. They're all distinct, and so the result is false. And we'll go down a bit. How about this one? So the element 25 appears twice. The element 75 appears twice. Well, either of those by themselves would be enough to return true, and so the algorithm returns true. The algorithm that solves this problem has no obligation to find any particular pair of duplicates. It just has to make sure that if it returns true, there is a pair of duplicates somewhere in the array. That's it. So that means that it could decide, once it's found one pair of duplicates, if it finds the two 25s, it could just immediately return true. There's no need to go around and find the 75 at all, because it knows the answer is true at that point. So one simple algorithm for this, and you'll notice the striking similarity between this algorithm and the one that I described a minute ago for pair sum 225. One simple algorithm uses 2 nested loops. So it just iterates over every index of the array using a variable I, and then for each possible value of I, it iterates over every index of the array with a variable j, and then once it has a particular pair of I and j values, just ask the question, am I looking at 2 indices that are distinct, so is I not equal to j, and is the element in index I equal to the element at index j? And if the answer to both those questions is yes, then it returns true, and it's immediately done because it's found duplicates and it can stop the loops immediately and return. And if it gets all the way to the end without ever having reached that return statement, well then I guess there are no duplicates, and so it returns false. I've chosen this as one of our introductory examples because although if we wanted to be really completionist about this, we could now write a proof, we could write an induction proof or something that proves that in all cases, this algorithm does indeed return the correct answer. I believe this is an algorithm because it's basically a first-year programming exercise that is intuitive enough that it shouldn't be controversial to argue that the algorithm is correct. And I've started with a very basic solution for that reason. But it's true that as we get into more advanced techniques, and certainly as our algorithms begin doing less intuitive things, it is up to us to demonstrate to anybody who wants to know that our algorithm actually does work. Now, one observation that we can make about that process, about those 2 nested loops, is first that because we're iterating over all I and j, there will be a few cases where I and j are equal, and we're going to skip over those cases, which is a little bit of a waste of time. But also that I can foresee a situation where I iterate through and there's a place where I is equal to 1 and j is equal to 4. So I consider the pair 6, 187. Okay, and I mean, they're obviously not the same, so it's not a duplicate. Great. But then later in the algorithm, I is equal to 4. And I iterate over all possible indices j, and I get j being equal to 6. Okay, so then I consider the pair 187, 6. And this seems a bit inefficient. It seems unnecessary, because obviously this is still not a pair of duplicates. Nothing's changed since the first time I looked at it. I guess I'm looking at them in reverse order now, but that doesn't make any difference. So it feels like by iterating over all possible indices I and all possible indices j, I'm doing more work than I need to do. I'm sort of doing twice as much work. I'm looking at every pair twice instead of just once. That's one observation I can make about the basic algorithm. And so I can try to adapt that observation into my code, into a specification of an algorithm that avoids doing that extra work. And if I do that, I come up with this. So here I'm iterating over all values of I, all indices I. But for each index I only iterate over a subset of indices for the value of j. And I can illustrate sort of what I mean by this. So suppose I is sitting at index 1. Well, what I'm going to do is, for j, I'm only going to have j span the values that are greater than I. So I'm going to have j be 2, 3, 4, and 5. And the idea is all the other values, so in this case, the values that are less than I, like 187, I'm sure that the pair 187 and 6 would have been considered earlier when I was set to 0 and j was set to 1. So the idea here is I'm hopefully avoiding doing double the work by only looking at indices j that are greater than I. A nice side effect of this is that because I know that j will never be equal to I no longer actually have to ask the question that whether I is not equal to j, because that's always going to be true. So all I have to ask is index I of the array, the element that index, equal to the element at index j of the array? Okay, that's one observation that I could make if I'm concerned about the efficiency of my algorithm, about doing as little work as possible, about getting an answer as quickly as possible. Another observation that I could make, it's a bit more far-fetched, but it has to do with a fantasy world where my array is much better behaved. So suppose I'm lucky, and you can guarantee me that the array that I get will always be sorted. Now, you can't guarantee me that because the problem specification that we saw a few slides ago, we'll go back and find it, the problem specification that we saw does not say that the array is sorted. It says it's an array of n integers. And of course, that means you can't assume that the n integers have any particular structure. You can't assume that they are within any particular range beyond reasonable assumptions about the word size of a machine you might be implementing it on or whatever. And so we can't assume that our array is always sorted, but suppose that it was. If our array was always sorted, then any pair of duplicates would have to be right next door to each other because they're in sorted order, and that means that they can't be too far apart. And if that's the case, if the array is sorted, that means I could find the duplicates by just sweeping from left to right. And at each step, with each index I just look at index I plus 1. And then if the two indices have the same element, then there are duplicates. Otherwise, there aren't. There's actually no need for a nested loop. Okay, but unfortunately, the version of the problem that I'm solving doesn't let me make that assumption. I have to assume the array is in some arbitrary order. But on the other hand, I suppose arrays can be sorted, can't they? So how about this version of the algorithm? It takes an array A, it gets its length, and then it sorts the array. Okay, I'll come back to that in a minute. And then after sorting, it iterates with one loop through the indices of the array up to the second to last index. And at each step, it just, so to recap the diagram I had a minute ago, at each step when I is set to a particular index, it inspects index I and index I plus 1. And if they're equal, then we have duplicates and it returns true. And if not, then if we get to the end of the loop without finding any, then there weren't any duplicates and it returns false. So the idea behind this is that although I can't assume the array comes in sorted, I could always sort it myself. And maybe by doing that, I get some benefit from the fact that when I'm done, the actual search for duplicates becomes, I don't know, I want to say a lot easier, but we don't really have any reason to believe this is any easier than what we were doing before, but that's just my intuition at this point. Now, one benefit of using pseudocode is that I can just write sort A. And again, it's up to me to ensure that when I do this, when I take liberties, that I'm taking liberties on something uncontroversial. I think that this is uncontroversial for the following reasons. One, I think we all know that arrays can be sorted. I mean, we're going to study sorting algorithms, so whether you believe me now or not, you will believe me soon enough. but because we know enough about programming by now, we probably have seen sorting to some extent in a first-year course, we know that arrays can be sorted. Okay, so that's one thing. The other thing I want to argue is that in all the languages you're likely to know, sorting an array is something that's relatively straightforward to accomplish with the language. So in any major language I can think of, so C++ or Python or Java or C, there are ways of sorting the array basically built into the standard library. And even if there weren't, it's relatively easy to find code to sort arrays or to look up algorithms for sorting. So sorting is a solved problem. It's something we know is possible. Now, we don't necessarily know how fast it is and other various efficiency-related concerns, but certainly it's possible. So I can write sort A because it's something that's reasonable to assume can be done. I would argue that the ability to do this is great because, and it's one of the benefits of using pseudocode. If we were using an actual language, Python or Java or C++, I would have to write the code that would, let's say, call the built-in sorting functionality of the language. And if you're a Python person, you know that can be done in pretty much one line. And if you're a C++ person or a Java person, you know that that can also pretty much be done in 1 or 2 lines. If you're a C person, then you're probably sobbing quietly because in C, you can sort arrays with a standard library, but it's a bit of a nightmare even if you love C, and I really love C. But even if sorting is straightforward within a language, we don't necessarily want to focus on minutia of syntax when we're talking about algorithms. Just writing sort A is great because it helps the reader understand that sorting is a secondary problem here, that really the important part of the algorithm is this, the thing that's doing the task we were actually setting out to do. The other thing to observe is that even if sorting is an easy thing to do in your language of choice, there are things in your language of choice that are ugly. And we really don't want, when the time comes to talk about those operations, to find ourselves unable to analyze algorithms because the code is so ugly that it's overwhelming to us. So pseudocode gives us a way around that. It allows us to decide, to make the executive decision that that array sorting is a solved problem and that everybody agrees it's possible, so we just write sort A. Okay, so we now have 3 possible ways of solving this contains duplicates problem. So I have 3 algorithms. I haven't written any code yet. All I've done is describe the algorithms at a high level. So suppose I need to solve this. Suppose I have a bunch of data, a large number of different arrays, and I want to solve this. Or suppose I'm writing code for some product or something that might need this as part of its functionality. I haven't written the code yet, but I'm considering it, and I want to choose an algorithm to use. Well, I don't need all 3 of them. I just need one of them. So what do? Well, I guess the question is, which one of them is the best? Okay. Well, I'm going to answer that question with a question. What does best mean? So which is the best? I don't know. What does it mean for something to be the best? The fewest lines of code, the least amount of typing, the compiler takes as little time as possible? No, probably not, frankly. When I said best, I'm sure we all, internally, all of our brains flipped to the same frequency and thought, well, best means fastest. Because as I said earlier, we do get pretty bound up in the idea that a better algorithm is a faster algorithm. Okay, whatever. So suppose that that's how you define best. Okay, but wait, what does it mean to be the best in that sense? To be the fastest, okay, taking the least amount of time. But in what sense? Always the fastest? Never slower than a certain amount? That is, does it take 10 seconds on average? Does it never take more than 10 seconds? How do I know? And also, how do I measure that? What does it mean to measure how fast something is? That's rough, and these are questions we need answered before we can make informed decisions, but frankly, before we can even generate any data. So I have to start somewhere. Okay, how about this? Let's implement each algorithm. We'll implement all 3 of them in the same language to allow a fair comparison. Then I will measure the running time of each implementation on various input arrays, and we'll just see what we come up with. All right, here are 2 tables of numbers that are the result of performing this set of timings. So what I did was I wrote what I considered to be an optimized C++ implementation of each algorithm. And frankly, the reason I chose C++ is that I like it. And I ran each algorithm on 5 different input arrays of size 500,000. And we should get used to the idea that n, the variable n in this course, pretty much always is a stand-in for input size. So when I talk about how does this algorithm perform on a particular n, well, n means the size of the input. So I ran it on 5 different arrays with n equals 500,000, and I ran it on 5 different arrays with n equals 1 million. And the results are summarized in these 2 tables. So what I can observe is first, I've decided to call the original algorithm I came up with, we'll just call that the nested loop algorithm. The nested loop algorithm where I avoided that extra work, we'll call that the improved nested loop algorithm. And then finally, this third algorithm that involves sorting, because it sorts the array and then walks from left to right, scanning over it, I'm going to call that sort and scan. But these are just arbitrary names, just so we have something to call them. So the first observation I can make looking at the data is that indeed my improved nested loop algorithm is in fact faster than the original nested loop algorithm. And that should comfort me a bit because, of course, it's the same basic framework but with a few less operations being performed. However, I observed that the original nested loop algorithm considered every pair twice. So there's 186, 187, and 187.6. And my improved algorithm only considers each pair once. So you'd think that that would speed it up by a factor of 2, but it doesn't. Instead, I noticed that my original nested loop algorithm comes out to about, on average, 0.0009 seconds. And the improved algorithm is faster. It is respectably faster, but it is not half the total time. If I go up to n equals 1 million, I see pretty much the same thing. So interestingly, I noticed that even though I noticed that I've got my input size of 500,000 and my input size of 1 million. I have doubled the input size. I noticed that in fact, the average running time pretty much doubles. Not quite, but pretty much. And the fact that 0.007 doesn't become 0014, that could just be a rounding error or something, but overall it follows that trend and that makes some amount of sense. On the other hand, the median doesn't seem to behave the same way. And what we're noticing really is a sign that when we begin analyzing data, which is collected over the process of running a program versus talking about an algorithm in an abstract sense, we could be capturing all sorts of weird correlations beyond simply which algorithm has more operations and which one doesn't. Okay, so I've got that observation that the improved nested loop algorithm seems to be an actual improvement over the basic one. I also noticed that my sort and scan algorithm is way slower than both of them. It's definitely way slower. And interestingly, its running time is very consistent. Notice how it is within one decimal place, so 0.0001 of all of each of the trials is within 0.001 of the others on this. And over here, they're all clustered around 0.0550. So it's got a very consistent running time. Also notice that the running time does pretty much double as I go to twice the input size, so that doesn't surprise me too much. But it's way slower than the other two. And we could reason about this. We could make up hypotheses for why this is. My guess is that sorting the array is probably a complicated task. By my intuition, it seems like looking for one pair of duplicates is less complicated than sorting the entire array. So of course, I guess it makes sense that the sorting-based variant takes a lot longer. So the question then is, based on the data that I've compiled above, what can we conclude about which of the three algorithms is fastest in general? And the answer is that we can conclude basically nothing. What we could conclude is on array 1, on my machine, the time that I ran this experiment, the nested loop algorithm came out with 0.0013, the improved nested loop algorithm came out with 0.0010, and the sort and scan algorithm came out with 0.0261. I mean, all I can conclude is basically what the data actually says. I can't really infer anything general from that information. And there are a lot of reasons for this. I'm going to unpack a few now, the most obvious ones, the most suspicious ones, but there's going to be reasons even if we clean up our experiment a bit. So first, I'm about to say some sort of mean things about timing experiments, so I want to make it clear that I love timing experiments. They are great. They are a critical part of assessing performance and optimizing code, and I use them all the time. And a lot of the work that I do, I have to use timing experiments. I have to run hundreds or thousands of timing experiments as I work to optimize code, to tune code for high performance. Typically, though, I do that at the end of the development process. I might design an algorithm. I then determine which of the possible algorithms is the best one via methods we have not seen yet. I implement the best one. I then use timing and other factors to instrument my code and profile it and decide how I can speed it up if performance is critical. And one of the reasons timing experiments can be helpful is they capture a lot of information beyond simply, oh, which algorithm has good performance. They actually capture information like, well, which implementation is treated the best by the processor, because processors inherently, there are differences between different processors and which operations take longer than others. So although timing experiments are nice, we don't know a lot of things about this data. And some of the things we don't know are sort of alarming. They're omissions that we really should know about before we draw any conclusions of any kind about anything. First, who wrote these implementations? Okay, well, I did. And then why was C++ chosen? Well, I already said that. It's because I like it. Did the author actually know C++ well enough to write good C++ code? The trend here is basically, what if it turns out that I just wrote a really bad sort and scan algorithm, and then it had bad performance? Is that the algorithm's fault, or is it my fault? So is it possible that the person who wrote these implementations had no idea what they're doing? And the answer is you have to draw your own conclusions about my competence, but certainly if I were to give you my code, that would provide some way for you to audit what I came up with. Was the experiment designed by somebody with a vested interest? So, I mean, I could give you my code as a way of proving to you that I'm competent, but is there any other way I could have influenced the results of this experiment? There are lots of people out there, and I don't want to single anybody out, but certainly being at a large university, this has come to my attention a few times. It seems like it's very easy for people that aren't properly informed or don't have time to become properly informed to fall for marketing tricks that they should be able to they should be able to see through pretty easily. I've seen a lot of pieces of bad software purchased because basically somebody from sales from the company that sold the software gave a good presentation. They showed off some slides that looked really slick, and somebody bought their software, and the software was then a complete nightmare. The problem is, it's very easy to concoct some way of making any of these three algorithms look good. And if the experiment was designed by somebody with a vested interest, how do you know they didn't do that? Also, how were these input arrays chosen? All I've told you is that on array 1, the sort and scan algorithm had worse performance. Have I ever told you what array 1 actually is? And then a mundane aspect, which is, what computer was I running this stuff on? What compiler was I using? It's possible that could have some impact, maybe only a minor one, but maybe a major one on how the code performs. And the question then is, could the choice of platform have some effect on the outcome? Okay, so I guess I can try to address some of these questions. These are questions you should have whenever anybody tells you about any of these experiments. Even if you have every reason to believe they were acting in good faith and everything was done properly, the ability to always be asking these questions in the background is part of what prevents you from falling into the trap of believing in a sort of scam, falling for slick marketing instead of actually scientifically evaluating your options. So what can I tell you about this? I'm going to skip to this one. First, I actually did write what I consider to be unbiased, optimized C++ implementations of each of the three algorithms. And I did actually time them. I didn't make these numbers up. These are actual timings that were gathered by me in what I believe to be a controlled setting. But this was a rigged experiment. It was rigged. How did I rig it? Well, actually, what I did was I chose specific input arrays. So I chose 10 input arrays that happened to cater to specific strengths of the nested loop algorithms. And you can see that I was successful because the nested loop algorithms look pretty good in the comparisons. And so it looks as if the sort and scan algorithm is behaving poorly, but actually it's because I rigged the experiment by choosing the input data so that the nested loop algorithms look better. Everything else about the experiment was done by the books. And so I'll go back to this slide. As with any scientific experiment, and although you could argue an experiment that wasn't conducted in good faith doesn't count as an experiment or whatever, but one of the fundamental requirements of something being scientific is the ability for it to be reproduced. That doesn't mean that every experiment has to provide to you every single aspect of how it was conducted, just that you need to know enough about the methodology that you could set up a parallel experiment that could help you verify or refute the conclusions. So, of course, unless you know enough about the conditions of the experiment, and those are given to you, and of course that you can trust the experiment was conducted in good faith, then you should be suspicious of the results. Even if you shouldn't be suspicious of the results, even when you know that these conditions are met, you still can't generalize the data from the experiment in a broad sense. You have to be very careful about doing that, and we'll see that for algorithm timings, although timings are useful, we can't usually use a set of timing data to actually conclude that one algorithm is always better than the others. So I chose input arrays that induced a specific outcome. Now, I also should add, maybe it's clear that this must have happened, but I chose input arrays carefully enough that it probably wasn't obvious that that was how the experiment was rigged. Even the skeptics in the audience that probably saw this coming and were wondering for a variety of different reasons why it is, like, we're wondering whether there was something strange going on here. Maybe you didn't single out the input arrays as the source of the problem. And the reason is because I took some care to choose input arrays that were different enough that the timing data was a little bit noisy. I mean, they're real timings, but I made sure to choose input arrays that looked a little bit more natural, so it wasn't clear that I had rigged the experiment that way. I could have rigged it in such a way that all of the nested loop algorithms finish in like 0.0001 seconds on every input, but that would have been a little bit too obvious. Keep that in mind. It's very easy to construct misinformation. If you know what you're doing, you can construct misinformation to support any conclusion you want to support. And it's worth considering this is misinformation. That's a term that wasn't in wide use until relatively recently, but now it is. We all know what misinformation is, and that it's everywhere, and that people fall for it. It's very easy to fall for misinformation if the misinformation is constructed the right way and fed to you in the right order. And part of being scientific is resisting that urge, is always constantly asking yourself, is this information I'm witnessing, is there anything about it that I should be suspicious about, or I should be asking more questions about? It's also true that people perform experiments all the time that end up having flaws. That's not misinformation. Experiments being flawed is part of science, but also part of science is being willing to question experiments, even if you really trust the person conducting them, being able to ask questions like, did you consider this case? How did you resolve this concern? Because that results in better scientific outcomes for everybody, for the entire scientific community. But keep in mind that somebody acting in bad faith, somebody who wants to sell you something, can set up a very authentic looking experiment that has pretty much whatever result they want if they are determined to do so. Okay, so what should we do? Well, I guess we could begin by conducting, a real experiment. We could try conducting an experiment that stands up to some degree of scientific rigor. So we'll start with that. And of course, I'm limited in the number of details I can provide on my slides, so I'll give a summary that I hope is enough for you to be able to recreate the experiment. I'll also post my code and you can take a look at it. So I implemented every algorithm in C++ following C++ best practices. That is, I wrote it in a way that I believe a competent C++ programmer would write it. In the sort and scan algorithm in particular, because it requires sorting, I chose to use the built-in sorting functionality of the C++ standard library. Now, the reason for that is twofold, one of which is if I had written my own sorting algorithm, my own sorting implementation, then you could reasonably ask the question, what sorting algorithm did I use? Was there a reason that could have affected the outcome? If I chose somebody else's, well, first, this is a standard one, so you could go and use it. You could look at it yourself. But second, I assume that the writer of the C++ standard library implementation I was using is probably an expert on sorting. They probably knew what they were doing. It probably was a collection of different people, and therefore I can assume that this is a optimized general purpose sorting algorithm, and therefore that it was probably competent at its job. Then, for a variety of possible input sizes, ranging from about 1,000 up to 1,000,000, there's a chart in a couple of slides, 10 arrays were randomly generated. Of those 10 arrays, 5 of them did contain duplicates, and that means the algorithm returns true, and the other 5 did not contain duplicates, so the algorithm returns false on those. I'll come back to that in a second. Then, to actually perform the timings, the timings were taken on the function that contained the algorithm only, not the part of the code that created the arrays, not the part of the code that printed out the output data, just the part that ran the algorithm itself. Only that was timed. I used the built-in high-resolution timing in the C++ standard library, again, for transparency's sake. And then I compiled it with G++ version 11.4.0 on a machine I have that was running running Ubuntu 22.04, and this was the processor on that machine. And of course, there are some details missing, like how much memory, what kind of disk was used, and those could be relevant. But the hope here is I provided enough that there are no obvious ways I could have manipulated the results. Although, of course, if I were acting in bad faith, I could have been lying about all this stuff. So, if you believe somebody's acting in bad faith, don't believe anything they say, no matter how much detail they give. I want to talk a little bit more about this. This isn't something we care about in the context of this course very much, but it's an interesting sort of scientific topic to talk about. How did I randomly generate 10 arrays? Okay, well, how do you randomly generate an array? Well, here's an array of size 5. Well, what I do is I use a random number generator, and I just generate 5 random numbers, and I put them in the array. These are what I consider to be random numbers. Okay, there they are. But how do I generate a random array that contains duplicates? Or a random array that doesn't contain duplicates? I'll start with the second case. So in the second case, if I want to generate a random array that doesn't contain duplicates, I will do this. I begin randomly generating numbers. Okay, so I generate 3 random numbers. Suppose that when I generate the 4th random number, it's the number 10. That's something I've already seen. And so I just keep track of numbers that I've already generated. And if I generate a number that I've already seen before, I ignore it and generate a new one. And I just keep generating a replacement until I get one that I haven't seen before. I don't try anything more clever than that. I just use I just discard anything the random number generator generates that isn't that doesn't meet my requirements. Because if I try something else, if I, for example, said, "Oh, you gave me the number 10, I can't use that. I'll subtract 1 and get 9." Yeah, but that's not quite random, is it? Because I'm always subtracting 1. So it's better just to throw it away and start again. And then I keep doing that until I fill the array up with values that I have not yet seen. What about if I want to generate an array that does have duplicates? That's a bit tougher because I could just generate any old array and then add some extra elements to it that are duplicates of previous ones, but that would be biased. That wouldn't truly be random. So instead I do this. Let's say I'm making an array of size 5 again. I generate 5 random numbers. I look at the result. If it contains duplicates, I just ignore it and I start over again. And I just keep starting over again until it generates, actually I would start over and generate different numbers just to be clear. So there's 7, 9, 15, 196. I just generate random numbers over and over again until I get a full array that does not contain duplicates. And then I use that. I just throw the whole thing away and start over again if it contains duplicates. And that way, again, I'm not building in any accidental bias into the preparation of my arrays. Okay, so I did that. And there are 10 arrays for each input size, 5 with duplicates, 5 without. I'm going to summarize the data in a bunch of different ways. So here on this slide, I have the 2 tables of data for the specific input size n equals 100,000. The first table is the situation where is the 5 input arrays that do have duplicates, and that means that the algorithms return true on each of these, and I did verify that all of the algorithms gave the correct answer. And the second table is the situation where the arrays do not contain duplicates and the algorithm returns false. All right, so what can I see? The first observation I can make, again, is when I compare my improved nested loop algorithm to the original nested loop algorithm, again, it is respectably faster. So if I look at the mean and median, and actually across the board it is always faster, but if I look at the mean and median, okay, 0.043030. So it took about, give or take, about 2/3 the amount of time. So even though earlier I was hypothesizing that I could save half the work, it turns out I'm only getting it down to about 2/3 the amount of work as before, on the specific case where the array does have duplicates. On the other hand, if I go down to the array that doesn't have duplicates, I'm getting an average of about 3.5 seconds, and that's pretty consistent for the original nested loop algorithm, and then 1.4 seconds, so significantly better than twice as fast. And again, that's also pretty consistent across them. So that's not influenced too much by outliers in the data. So it's weird that we originally thought maybe I could save half the work, but once I break it down into with duplicates versus without duplicates, it does maybe average out to about half the work, but in some cases it's way faster, in some cases it's not as much of an improvement of performance. If I look at the sort and scan algorithm with n equals 100,000, I notice that despite the fact that it has to sort the array, which we think of, at least intuitively, as being sort of difficult compared to just looking for duplicates, even though it has to do that, it's really fast. It is decisively outperforming the other two algorithms in both tables. Also notice that it's got a very consistent running time. Other than this case here, it's pretty much always sitting around 0.0047 or so. It's unclear what happened here. We could maybe reason that because that's an outlier, because that's way different than all of the other cases, it could be that maybe there are some random factors involving the timing experiment that affected this. So maybe something going on the machine on which the benchmark was running affected the running time of the trial. And we can assume that probably happens to every trial with some random probability. So maybe 10% of all trials have some minor effects that are to do with the cache performance of the machine or what the OS is doing in the background. But overall, the sort and scan algorithm is decisively much faster. This slide shows I still have the table with duplicates. I have the table for n equals 100,000, but I also have the table for n equals 1 million. So I'm comparing two different input sizes, both of which are the benchmark with duplicates on this slide here. And so compared to the n equals 100,000 case, when I'm thinking about scaling up the input size by a factor of 10, what I notice is, okay, so I was taking about 0.45 seconds on average when I worked with 100,000, and now I'm taking about 1.07. So that's about, 2.5 times larger, which is nice because I increased the input size by a factor of 10. So I have 10 times as much input, and yet I'm actually only taking about 2.5 or 3 times as much time with my nested loop algorithms. Same thing here. So 0.3 versus 0.83. So that's maybe 2.5 or 3, somewhere around there. Definitely not 3 times as much, but somewhere between 2.5 and 3. If I look at the sort and scan algorithm, I'll notice that it takes, as we saw, 0.0047 seconds on average, and that's a pretty tight, it's clustered pretty tightly around that. And if I look at on a million, it takes just over 10 times as long, maybe 11 or 12 times as long. So I scale up the input by a factor of 10, and the running time scales up by a factor of just over 10, which is interesting. Now here are two tables with the results of n equals 100,000 and a million with the two sets without duplicates. So 100,000 without duplicates and a million without duplicates. Okay, so here again, as we saw before, the nested loop algorithms take about 3.5 seconds for the original one, about 1.4 seconds for the improved one. And if I increase the input size by a factor of 10, I get these numbers. So I go from 3 seconds to 300 seconds. And what's really interesting to observe about this is it looks like it's almost exactly 100 times the total running time. So 3.58 to 358. There isn't really that much noise. 1.39 to 139. It looks like I'm just multiplying all of the numbers by 100. And that's sort of nasty. That's really worrying, actually, because back here, it makes sense that as the input gets bigger and bigger, the algorithm is going to take longer because when I have more data to work with, it takes longer to process it. And I'm willing to put up with, if I increase the input by a factor of 10, I wouldn't mind it if the algorithm takes 10 times as long. That makes sense. But I don't know if I like it by going up by a factor of 100. If I increase the input by a factor of 10 and I get a running time increase of a factor of 100, that does not bode well if I keep increasing the input size. And remember, a million is not a big number. A million is the kind of input you would work with a lot in a first-year programming course, frankly. A lot of the code you write in first-year programming can make quick work of 1 million elements. That's not a big number. That would be 4 megabytes of integer data. And so if I'm getting this huge explosion of running time, just working from 100,000 to 1 million, that could be pretty dangerous. Danger could be on the horizon if I want to begin working with 10 million or 1 billion elements. On the other hand, if I think about the sort and scan algorithm, okay, it goes from 0.005 to 0.05. It scales up by just over a factor of 10 again. So it's very consistent and it reliably scales up more or less in line with the amount that I'm scaling up my input size. I can make a plot of the data that I collected. So I collected data for n equals 1,000, which is somewhere around here. N equals 100,000, 200,000, 300,000, 400,000, and so on, all the way up to 1,000,000. And for each of those, if I look only at the case where it does contain duplicates, there are 5 arrays each for each of the different input sizes. And what this plot is showing is the average running time among those 5. We saw from the tables that usually averaging it out, if we look at the mean, it does seem like the mean is a reasonable representative of the times for the 5 arrays. I mean, there can be some departure from that, but it looks like the mean is something we can rely on as a representation of how long things take. So the plot here is just plotting the mean across the 5 arrays for each different input size up to 1,000,000. And we'll observe that the sort and scan algorithm is just doing great on pretty much all of the inputs. It's barely distinguishable from the 0 line at this scale, whereas the other algorithms jump around quite a bit. And this could be for a variety of different reasons. It probably has to do with the fact that the 2 nested loop algorithms return early if they find duplicates. And so the earlier they find the duplicates, the less time they take. And that could, of course, change the average. That could have an effect on the mean. And if we go back actually to the table where we look at the case where the array has duplicates, you can sort of see that happening. You can see that if I look at n equals 100,000, there's one array here where they take 0.9 seconds and 0.6 seconds, respectively. And there's one over here where they take 0.1 and 0.08. And that's probably because this array was just easier for those algorithms to work with, whereas this one, the duplicates, even though they did exist, were somewhere later on in the array and it took longer to find them. And so that can affect the mean, and so maybe all of the 5 arrays generated in this case were sort of unlucky. They took a bit longer. And all of the 5 arrays in this case were just really good inputs. They just had duplicates really early on. So it's hard to draw too much. Even if we could draw conclusions from timings, it's hard really to know what to make of the running times of the red line and the blue line compared to the green line, of the 2 nested loop algorithms versus sort and scan. However, we can still see that the improved nested loop algorithm is reliably sandwiched between the sort and scan algorithm and the original nested loop algorithm in all cases. Now, if we begin looking at the case where the array does not contain duplicates, we do notice what appears to be a trend forming. So the input array doesn't contain duplicates, and we can see that the sort and scan algorithm here is still hugging the x-axis, like it's still basically just sitting there, almost 0. At this scale, it's hard to tell it apart from 0 because we're not talking anymore about 2.5 or 3 seconds. We're talking about 350 seconds. When I look at n equals 1,000,000, the original nested loop algorithm is taking, I'm going to ballpark that at about 360 seconds to process, versus the, as we saw, the sort and scan algorithm is still taking under a second. That's a pretty big deal, and this should be a warning to us. It turns out we can't make that much of these timings otherwise. We can't generalize what the timings are telling us, but certainly when the timings point towards bad news, we should take that into account. This is still showing, of course, that the improved nested loop algorithm is still doing better, but its performance is still pretty bad. We're talking about 1,000,000, something that this algorithm, the sort and scan algorithm, can solve in less than a second, and it's taking now a couple of minutes for our improved nested loop algorithm to solve this. That's worrying. So the question then is, we did a more rigorous timing experiment. We spent quite a bit of time on detailed analysis of the data. We viewed the data in various ways. We came up with some hypotheses for why some algorithms are slower than others. The question then is, what can we conclude from our experiment about which algorithm is best? And the answer, once again, is nothing. Unfortunately. We can draw a lot of useful conclusions from the data. We just can't use the data to conclude once and for all which algorithm is best. So just a reminder, because I want to make sure it's clear that I'm not against timing experiments, it's good to have this data. Among all the various other ways you could use the data, we have, if I needed to optimize some code. If I've written code and I want to optimize it, I could use performance profiling to do high resolution timings and localize those timings to find which parts of my code are taking the longest amount of time. That's actually an interesting topic. I love talking about it, but it's not really a topic for this course. If I have one algorithm that I've implemented in different ways, maybe in different languages, but not necessarily, I've made different decisions of which types of loops to write or the order that I do certain operations. If I'm choosing between different implementations of the same algorithm, then timings are a great way to break the tie. They're a great way to figure out which implementation performs better. I'm still subject to the fact that I'm only really getting data about the inputs that I test, so I have to be very careful about which inputs that I test. But it is a good way to distinguish between algorithms that are otherwise tied. Similarly, even if I have different algorithms that have the same or similar asymptotic performance, so we don't know what this word is yet. We will know what this word is soon. But bear with me until we know the definition of it. If I have different algorithms that are tied by our usual analysis method, so we're going to do something called asymptotic analysis to figure out basically how long algorithms take in a broad sense. If we have a variety of algorithms that are tied, a timing experiment is a great way to break the tie, to figure out, to get some intuition about which algorithm requires less overhead in general. And we'll come back to that a few times throughout the course. Sometimes when I'm designing algorithms, before I even have an algorithm that I'm finished with, I might write some code and do some timing experiments just to help me wrap my head around the problem. And there are times, even when making these slides, when I wondered to myself how long something would take, where frankly, it's pretty easy to run an experiment. I could just go run an experiment and just get an idea about whether the assumptions I've been making make sense. I could use timing experiments to validate theoretical conclusions. Now, be very careful what I mean by the word validate there. If I write a proof of something and the proof is correct, then the thing I've proven is true. It is true 100% of the time. It is a universal fact. I do not need experiments to validate a theorem that I've proved, to verify that it's correct. However, I can use experiments as a way to give myself some reassurance. I've written a proof of something. I believe the proof is correct. Before I go show it to anybody and run the risk of embarrassing myself, I do a bit of experimentation just to make sure I haven't gone down the wrong track and missed some obvious detail. So the validation there is basically just so that I can sleep better at night. And of course, timings are a great way of determining how certain factors that are independent of the quality of the algorithm affect the performance of my code. So things like cache behavior on a specific architecture, the compiler I'm using, and whatever. Timing is great as a way of resolving the impact of those factors. So remember, as I said earlier, even in the cases where timings are useful, be careful about believing timings somebody else provides you unless you know enough about the context to trust them. Even if you assume that the people you work with are being honest and they're acting in good faith, because if you can't assume that, then just don't believe it, frankly. Even if the people you're working with have done the experiment properly, they could still have missed something, or it could be that the experiment isn't applicable to your specific use case, and so be careful about that. Now, a lot of the timing experiments you see done on actual code, again, this is a topic not really that relevant to this course, a lot of the timing experiments you see out there are done as part of automation, which means you can easily just run them yourself, which means you can easily verify the data firsthand. But make sure you have that ability. Either you're given enough information that you can reproduce the experiment, or ideally, you're simply given the experiment and you can run it yourself. The data we generated, and in general experimental data, allows us to form hypotheses. It allows us to, in cases where we don't have theoretical conclusions that we can use, it gives us some backstop. It allows us to say, well, our experiments do show this, so this is an avenue that's worth pursuing or something. But in general, the experimental data doesn't really prove anything besides what the data itself tells you. We can say that on the specific arrays we used, the algorithm with the blue line, the improved nested loop algorithm, has performance that's about halfway between the other two. We can just read the data directly, and that's pretty much it. We don't necessarily know that means that this algorithm is the second best out of the three in all cases, although it certainly gives us a bit of a hint that it might be. It doesn't prove that to us. And we want to be able to make broad statements. I want to be able to say the sort and scan algorithm is the best one. And I want to be able to say that in a theoretically rigorous way. I want to be able to say that in a way that you will believe me when I say it applies in general, as opposed to it applies on these particular input arrays. It is, as I said, true, though, that if I do a timing experiment rigorously, often it does give us information that we can use to form a hypothesis. That is, it does give us a hint about how we should pursue the question of which one is better. And it turns out that, in fact, the data we have here that suggests the sort and scan algorithm is better is on to something, and that we have a way of proving that. It's just that the proof isn't generating a bunch of timing experiment data. So one observation I've already made a couple of times is that those nested loop algorithms, we've noticed they seem to do a lot better when the array has duplicates. And one reason I think this could be is that they return early if the array has duplicates, whereas if the array doesn't have duplicates, both of the nested loops have to run all the way through. So if we look at them, I can sort of illustrate what I mean. Here is the case where there are no duplicates, this return false at the bottom. We only get to that return false after doing tons and tons of work inside the nested loops. On the other hand, if I hit this return true during the loops, the function just ends instantly, which means if I'm lucky, and I think luck is the right word for this, if I'm lucky and you hand me an input where there are duplicates and the duplicates are relatively early in the array, then I don't have very much work to do. I can call it a day after looking at only a few elements and therefore appear to have a much faster running time. If the input array doesn't have duplicates, well, in a sense, that's sort of our worst case scenario. We have to do all of this work and it comes to nothing and then we return false. And it's interesting to think about the fact that if the array doesn't have duplicates, it doesn't really matter that much what specifically is in the array. I still have to do all the work and then get to the end and return false. So we can actually describe that. We can say an input array without duplicates is a worst case input because it results in the algorithm taking as long as it possibly can, the maximum possible amount of time. We'd say in this case it's a worst case input as far as running time is concerned. But again, I will admit that we do spend most of this course thinking of worst case in terms of running time. The worst case running time of an algorithm is the maximum possible running time over all inputs of a particular size. So obviously, if we just think of the maximum time the algorithm takes on any input ever, well, I just give you a really massive input. I really want to characterize the worst case in terms of the size of the array. So the worst case input for an array of size 1,000 or a worst case input for an array of size 100,000. I typically parameterize my worst case running time in terms of the size of the input array, in terms of n. So the worst case running time with respect to a particular value of n is the maximum possible running time of the algorithm on an input of that size. And an input that actually has that running time is then called a worst case input. And as I said at the very beginning, there are lots of other types of resources we could concern ourselves with. So we could think about running time, and yes, usually we do, but we could also think about memory or bandwidth or power consumption and lots of other things as well. And it's interesting to think about the fact that actually, of all the resources we work with, time is the one we have the most of. Because even if you give me an algorithm that might take 10 years, at least in theory, I could run the algorithm for 10 years. I might not want to, but I do have, I don't necessarily have that much patience, but 10 years, as far as we know, the world's not going to end. I could run the algorithm for that long. On the other hand, if my machine has 100 gigabytes of memory, and you give me an algorithm that requires 200 gigabytes of memory, then I just can't run it. So strangely, even though we obsess over running time, memory and bandwidth and power, those are actually resources that are a lot more precious. And there are times when we have to do analysis that amounts to proving that we won't need any more than a certain amount of power or bandwidth or battery or other resources that are relevant to a particular application. And there are even things like times when you have to argue that an algorithm doesn't need to write to disk any more than a certain number of times. We don't care how much it writes, only how many times it goes to disk. In applications involving database algorithms, that's often a very important constraint, although it's not something we're going to worry too much about in this course. While we're on the subject, we talked about worst case inputs, and it is true that we really spend a lot of time concerned with the worst case inputs in this course. It's worth considering what would be a best case input for these two algorithms, these two nested loop algorithms. Now, best case inputs are mostly a novelty. Nobody really cares about them because it really amounts to a best case input is basically what if you are the most lucky you can possibly be. Like, in the same way that I wouldn't, if I cared about the best case, I wouldn't have to worry about my finances, because the best case, I just win the lottery every time I play it. And for the same reason that I don't go out and buy lottery tickets because I assume that the best case is going to happen, we shouldn't necessarily get too wrapped up in the best case running time of an algorithm, because the best case might happen, but unless it's likely, we shouldn't worry too much about it. But what is the best case input for these two algorithms? Well, as I said, the algorithms have less work to do if they can return early, if they hit that return statement as soon as possible. So I think this array here would be a best case input. In this array, there are duplicates, and they are in the first two positions, which means pretty much in the improved algorithm, the very first time we hit that if statement, we're going to return true. So we only iterate through each loop once. We're halfway through the first iteration of each loop and we return. In this one, we do have to do a little bit of work. We have to go through a couple of iterations to get to a point where j equals 1, and then we return true. But that's pretty quick, and that would be a best case input. A task you can think about is to describe a worst case input for the sort and scan algorithm. Now, to do this, there is an unknown, and it has to do with me taking liberties with pseudocode, which is that you could think about this and realize that, it's possible that sorting an array takes a different amount of time depending on what the array looks like. Theoretically, at least, an array that's less sorted, that's more jumbled, might take longer. Or actually, it might take shorter for all we know. So for the sake of the exercise, let's assume that sorting the array A takes exactly the same amount of time in all cases for a specific size of array. So there's no way that the sorting procedure has an impact on what is considered a worst case versus a best case input. So see if you can think about what would be a worst case input, what it would look like for this. So one of the reasons we care so much about worst case running time is that if I can say, in the worst case, on an array of size 1 billion, this algorithm requires at most 10 seconds. So the worst case running time is 10 seconds. That is a way of you bounding the risk that you take by using my algorithm. If I were to tell you instead that the algorithm takes typically 10 seconds on an array of n equals, let's do 1 billion. If I told you on an array of size 1 billion, it typically takes 10 seconds. The average array takes 10 seconds. Well, that's nice to know. I mean, that means that if you feed in a random array, you should expect it to take 10 seconds. Great. But what if out there somewhere there's an array that takes 1 second? Well, that would be nice. That would be lucky. But what if out there's an array that takes 150,000 years? That would be a bit rough. If you're writing code, you don't want to invest too much in the assurance that on average it takes 10 seconds, because the tails of that distribution can be way off in the distance. It could be that on average it takes 10 seconds, but sometimes it takes 0.1 seconds, and sometimes it takes 1,000,000 years. And if you happen to hit one of those inputs where it takes 1,000,000 years, you're going to lose patience pretty quickly for that 10-second assurance. If I give you a worst case assurance, if I say in the worst case, it takes 10 seconds, well then you are assured that under no circumstances ever, in any situation with any input of size 1 billion, will it ever exceed 10 seconds. Maybe it takes 5 seconds. Maybe it takes 0.05 seconds. That would be great, but under no circumstances will it ever exceed 10 seconds. That's one of the reasons we like talking about the worst case, because it gives you an absolute guarantee. When you choose to use an algorithm in your code, you're taking a risk. You're taking a risk that the algorithm might take a long time. And if you can guarantee that the maximum length of time is 10 seconds, it could be that in your code you could say, actually, I need an algorithm that takes 0.01 seconds, so 10 seconds won't do it for me. But if you have no other choice, at least you know it'll never take 20 seconds. It'll always take at most 10 seconds. Now, we find in this course that seconds is a bit of a short-sighted measurement, because how long something takes depends on the characteristics of the processor, and those change all the time. We do, however, want some measurement that tells us, it gives us some absolute assurance that the algorithm will never take longer than a certain amount of time, or that the algorithm scales up in a certain way. And the idea of taking that risk is one reason why worst-case running times are an attractive option, because they give us the ability to make a guarantee. As a way to contextualize this, I want to talk about some things that we're not going to see for a while. In this course, we're going to study sorting algorithms. And two very important sorting algorithms are called Mergesort and Quicksort. And I will say this now, and I'll say it again in a few lectures, but these are just names that somebody made up. And Quicksort in particular, think of that like a brand name. Just because it says Quicksort and quick is in the name doesn't mean it actually is fast. You can get a lot out of things in life by using names that sort of result in people jumping to conclusions. So Quicksort is, you can see it's a proper noun, it's a brand name. Don't assume it's fast just from the name. However, I decided to I wrote my own C++ implementations of Mergesort and Quicksort, and I ran them on a bunch of randomly generated input arrays. I used the same methodology as the experiment we did earlier. I of course, didn't do the case with the arrays having duplicates or not. I just generated a bunch of random arrays. But for the sake of the argument I want to make today, I ran both algorithms on some randomly generated arrays, and I did a timing experiment. We discovered that overall, both algorithms are really good. I was able to sort my array of size 1 million in 0.08 seconds. That's pretty good. And overall, Quicksort demonstrated a pretty clear advantage. Not a major advantage, but a clear one. It is decisively a little bit faster than Mergesort. And one of the reasons for this, and we'll see this again when we actually talk about Quicksort, one of the reasons for this is because Quicksort just is able to do a bit less work on each iteration. As it processes the array, it does it in a more streamlined way. It's a bit of a simpler, more streamlined algorithm, whereas Mergesort has more moving parts. And so it makes sense that Quicksort therefore can save a little bit of work, a little bit of time. The problem is Quicksort has a weakness, a major weakness. If I feed in the wrong choice of input array, and one example of an input array that induces that weakness is an array that's already sorted. And you could look at that and say, well, then just don't give it sorted arrays. There are lots of other ways to induce this weakness. It's not an easy problem to patch over, but a sorted array is one easy way of inducing the weakness. Quicksort has this major weakness. If I give it an array that's already sorted, the running time absolutely explodes. So we were going from 0.08 seconds on an array of size 1 million to 300 seconds, or more or less, 290 seconds. That's a huge deal. And Mergesort doesn't have that sensitivity. It turns out that Mergesort basically always takes the same amount of time, give or take a little bit. So the overall behavior of Mergesort on any array of size 1 million is a stone's throw away from where it is on this chart here, pretty much. Now, I'm not saying that because I'm concluding that from the plot, just to be clear. I happen to already know the way this course is going to progress, and within a few lectures, we will all be able to prove that that's the case. So the issue is that Quicksort is generally pretty fast. It's actually so fast that it generally beats Mergesort. But if you give it the wrong input, if you give it one of its worst case inputs, it absolutely explodes in complexity. And that's a big deal. And that's risky. If you use Quicksort, you are taking a big risk, because what if one of the inputs you process happens to target Quicksort's weaknesses? And so a couple of questions I want to ask that we can think about. If you were writing some critical code, because maybe you've gotten all the way to this point in the lecture and you're still skeptical about why exactly we care about theoretically studying algorithms, if one day you find yourself writing some critical code that requires sorting, and you need to make sure this code is fast, and you do a timing experiment, and you happen to see this data. So you see this table, especially that second table there, which demonstrates Quicksort taking 290 seconds. Would you risk using Quicksort in your code after you saw that? And my second question is, okay, suppose you are writing code that required sorting. Wouldn't you deserve to see this? Wouldn't you want to know about this risk before you made that choice? I mean, certainly, I think once you saw that table, you might think twice about using Quicksort, but wouldn't you want to see that? Wouldn't you want to know that Quicksort has this risk that you're taking before you made the choice to put it in your code where potentially that running time could explode one day? And if the answer to either or both of those questions is yes, well then that's exactly why you need to study algorithms.